So hopefully part 2 of 713A. Going to get some proofs here. Just want to introduce these theorems a little bit. Hopefully it was easy to fill this in here. So you know you have two sides of one triangle. And the other piece of this is not just an angle, but an included angle, an angle between those two side lengths. Right, this is fixed. There's only one thing that would fit in between here to connect those two sides. There's only one length, BI. And that BI has to be the same as ET or TE over there to make this work. So if you have two sides and an included angle of one triangle congruent to the exact same thing in another triangle, and of course the conclusion is this triangle and that triangle have to be congruent. All their parts are congruent. BI is the same length as ET. Angle B would have to be congruent to angle T. You could match up all parts there and figure that out. Of course, another movie reference on here. Triangle Bill should be congruent to a correct letter order over there. And if you're careful about this, you can see that B is at the end of this side with the 1 mark on it. So is T. T comes first. I is the one across from the side with 2 here. Means got to be E. And L and D, of course, are the same ones that are congruent. So you got triangle TED. And if this was in a proof, your reason for this would be because of side angle side. And this is being rotated. It's being turned maybe 90 degrees, something close to 90 degrees to map one onto the other exactly. And I emphasize, I got the donkey here because if you write these letters in the wrong order, you might end up with a theorem that doesn't work. Of course, you know I'm talking about side-side angle. You would never write that in another order on there. But this does not always work. There's times where I can show you where a side on an angle is congruent to a side-to-side an angle, but the triangles clearly look different on there, which we'll talk about that on one of the examples later on. The next two postulates or theorems look very similar. This one's called angle-side angle. And again, you're going to see me write ASA on my answer keys later on. That's typically how it's going to show up in a proof. Take a minute to write down the vertices here, N, E, and W, P, T, and S, P, S, and T there. And we'll get it visually first, and then we'll add in some words to the sentence here. So first thing I got to give you is an angle. T and W are congruent. There's the first given. And this is another one where letter order matters. The S, the side, has to be between the two angles. So if I were to give you angle E congruent to angle S, there's only one side that's between those two. It's the one that connects this angle to that angle. I'd have to know that that and that are congruent. I believe I did this differently. I believe I did the bottom one. Angle P is the same measure as angle N. There's only one side that's included for that triangle. If I was in class, I'd say, hey, which side's the included one? ASA. ASA would always be paying attention to this postulate. ASA, which one's the included side? And of course, he'd say PT is included here. And he'd say that NW is included down here. Get another plug for that movie, Three Amigos. Steve Martin, Chevy Chase, and the other guy, I can't remember his name, Martin something, I think. So here's what it looks like in words. You had two angles, and not just one of the sides, but the included side, the side that's between them, of one triangle congruent to the same thing in another triangle. Two angles and the included side of another triangle. Same conclusion, you know that all the parts of the triangle are congruent. And of course, this is sort of obvious. If you know two angles are the same, the third angles have to be the same because of that third angle's corollary that we talked about the other day. Here's the letter order I chose. And somebody else could have chosen a different order, but they've got to have the letters match up. N in this triangle corresponds to P, so P has to be my first letter to name the other triangle. E corresponds to S, and of course T corresponds to W, so that's the correct letter order for that one. And of course, if this isn't a proof, that would be because of angle, side angle. It appears to just be slid up there, which is called a translation. Hopefully it'll show up here. There we go. All right, the last one is just a sort of variation of this. It's very close related to this. If you were to take out the third angle's corollary and say, hey, the third angle's corollary says that this angle has to be the same as that angle, you could prove that this could be angle, angle, side, or angle, angle, side instead. That's what the last version, the last alternative here is. So I'm gonna title this in a moment, but I want you to mark the drawing up first. We get M, H, and T. This is exactly how I do it in class. F, A, and V. With the given information, F is congruent to T. Somebody measured it. They know those are exactly the same. They constructed a copy of an angle. M is congruent to one of those, and you can tell by the scale of it that acute angle is congruent to that acute angle there, V, which probably gives you a good idea of what type of transformation it is. It looks like it's being flipped, so it's some sort of reflection. Now, I'm not going to mark the side in between like I did in the last one. I'm marking one of the other sides. Hopefully you can see that this is angle, angle, and a side somewhere else in the triangle, congruent to an angle, and a side somewhere else in the triangle. Same thing would have happened if I instead gave you this side, that one congruent to that one. Same idea. So either one of those examples of angle, side, angle, angle, side, which is the fourth way. So there's now 4 ways to prove triangles are congruent. The other ones are all theorems, just postulates. This one's a theorem because technically it's a proven variation of angle, side angle. So as you can get that into words on there, the first thing that came up was the 2 angles. The third part, and you always need a third part, is that side congruent to that side. Without a side length, you'd have no idea how big or small they are. Now, I'm using this term non-included. I've got to clarify it's not the one in between. This is a slightly different theorem or different reason for proving the triangles are congruent. To the exact same thing in another triangle, and I'm saying corresponding because it's the one that matches up with that one. This would not work if that side was marked. Because if you notice, this is across from the double angle here. This is across from the single angle. You couldn't prove those are the same. Those triangles would not have to be the same. They could be non-congruent. It's got to be the non-included sides that correspond to one another. And then again, same conclusion, the triangles are congruent. So finish that statement in the correct letter order. Take a look at your drawing, see what F corresponds to up here, see what A corresponds to, see what V corresponds to. And hopefully that order makes sense. Maybe this is your favorite theorem, maybe. And again, if it was in a proof, you'd see this is by angle, angle, side. And it looks like some sort of reflection happening there. So try these. There's 4 example problems on your paper. I'm going to give you some information here in a minute. I typically in class, I'll say, okay, can we prove those 2 triangles are congruent? Let's just do this first one together. And I wait for about 15 seconds. And somebody says, yeah, definitely you can. That's a parallelogram. And if it's a parallelogram, these sides are parallel, these sides are congruent. And they've jumped to like 9 conclusions before they've even had a chance to let me say, no, you can't prove it's congruent. You don't know anything about these 2 triangles right now. Take it back. You know one thing about these 2 triangles. I'm going to give you more information. I'm not going to tell you it's a parallelogram. I'm going to give you some given lengths on there. I know for a fact that this side and that side are congruent. Mark that on your drawing. I know this side and that side are congruent. That's all you've got. So see if you can do this one right here. Are those triangles congruent? And which of those, there's 4 theorems above, which of those 4 theorems would apply? And usually somebody will go, well, it's side, side, side. And I'd say that's correct. But you need a third side. And of course, the third side, listen carefully to this. There it is. The third side is a shared side. That was the only thing you had in the beginning until I added these marks on here. So these 3 sides are congruent to those 3 sides, which is why the triangles are congruent. In fact, it is side, side, side. I could later on go back and prove this is a parallelogram, but that's not a given for that one. This one doesn't have enough information. Nor does that one or that one. Not enough information right now. I'll add some stuff in here in just a moment. To clarify the ABC being isosceles, that's the vertex. And these are your base angles. Here's the rest of the givens. So this is a good spot to pause. Just so you're clarified here, I'm referring to the yellow triangles here. I don't care about the white part there. It's helpful, but not the triangle I'm focused on. And here I'm thinking about the green triangle and the blue triangle. Are those triangles congruent? Can you prove those two triangles congruent? I'm not referring to these two triangles, blue and green. But again, pause, see if you can get an answer for those three. Come back and see if you agree. This is usually a good discussion one. Right now, there's lots of ways to jump to valid conclusions without valid logic to get there. The yellow triangles are definitely congruent. You need a third part. You get this part and that side and that side. If you could prove these sides are congruent, you'd have side, side, side. There's no direct, clean way to get there. If you had an angle, you could get there. And hopefully you recognize that angle C and A are the base angles of that isosceles triangle. If the sides are congruent, the angles opposite them are congruent. If this was in a proof, you'd use the fact that you understand things about isosceles triangles. It's not the definition of that word. Hopefully remember back. There's my third amigo. Now, as you read things and you make valid conclusions, mark the drawings. Now I can see its side, angle, side. The other piece of this, if this was a full proof, would be remembering this is the isosceles triangle theorem, where isosceles triangles have two angles that are also congruent in addition to side lengths. Kind of a similar idea on this one. You've got a side length and a side length that are congruent. The heights are the same. They both have right angles. That's beautiful. The third part that's missing, a lot of people like to go after the vertical angles here. These angles are congruent, but they have nothing to do with these triangles. Most people recognize they share something. They have the exact same base on there. So if I use that part, should make sense. That's a side angle side proof. This could be done differently. If you wanted to write a longer proof, you could prove these lines are parallel because same side interiors are supplementary. If these are parallel, you could prove you have some other congruent angles on there. That's a much longer version of the proof. That's probably the straightforward version. And then we've got a trap set for you down here. A lot of people like to say this is side angle side. This is the classic example of something that's not side angle side. This does not work. We don't know anything about it. They could be, but we don't know enough information about them. I'll try to show you an example of it up here. I got to remember how this works. This is a good one to show you. Side angle doesn't work. I've got a side here. So you could justify that these three are the same. Sorry, those two sides are the same. This would give you a side. I'm going to erase those for a second. This would give you a side. Let's use one of those. Whoops. I don't think I can get that out of my head right now for a second here. I would have trouble seeing this. I'm going to come back to that when I can spit it out of my brain on here. I'm going to come back to that. I'll give you some information on the proof, and I'll come back and revisit. Got to settle my brain on that one. So you already have the letters on your drawing for that, I believe. Yes, you do. There's two givens, and I'll give those to you at the end of this. Step 5 of the proof. Prove the triangle ABC is congruent to that other triangle over there. And letter order matters. And you might be looking at it now and going, oh, I think it's a reflection. Or somebody else will go, no, I think it's a rotation. We don't know yet. Need some information on it. Need some given information. Well, one of those is that C and H are congruent. And when you read givens, mark the drawing with a valid conclusion as you go through this. The other given is a written given. Yes, you have to include written givens in this thing. B bisects CH. So there's one given, there's the other given. There's enough information you can prove those two triangles are congruent. It's a good spot to pause, try to get through the whole thing, see if you can prove those triangles are congruent. I'm going to stop it now. I'll be back in part 3 in just a moment.